In the mesh analysis technique, step number 3 is applying KVL in individual meshes. Let us understand KVL. KVL is Kirchhoff's voltage law or Kirchhoff's mesh law. It states that the algebraic sum of potential differences and the EMFs in a closed path is equal to 0. So when you are going around a mesh, so you start from a particular junction and go around the mesh till we come back to the starting point. The algebraic sum of the potential drops and the EMFs in a closed path is equal to 0. So let us see the sign conventions that we have to follow while writing the equations. So a convenient system is to go around any closed path. If we go from the negative terminal of the battery to the positive terminal of the battery. For example, you're going from A to B and the first terminal is negative terminal and the next one is positive. When you're going from negative to the positive, this we have to consider as negative. So I have considered minus 5 volts. But when you're going from B to A, it should be considered as plus, right? So similarly, if we go from the positive terminal to negative terminal, then this voltage should be considered as positive sign. So A to B, the first terminal that you come across is plus. So from A to B is plus 5 volts. It is important to note that the sign of the battery will not be decided depending on the current direction. It will be decided depending on the path direction. When you are going from A to B, negative means negative, negative to positive means negative, positive to negative is positive. So similarly, the sign of an IR drop, if we go through the resistor in the same direction as the current, means the path direction and the current direction both are same, then we have to consider that potential difference as positive potential difference. So give positive sign. So here A to B, the path direction is A to B, the current direction is also same. So I have given I into R1, V is equal to I into R1. So voltage potential differences plus I into R1. Similarly, if we go in the direction opposite to that of the current, then the potential difference should be given negative sign. So path direction is A to B, the current direction is opposite to that, the potential difference should be given minus sign I into R1. It is clear that the sign of the voltage drop across the resistor depends on the direction of the current through the resistor. Okay, consider the closed path AB, C, D, A. So this is the closed path. Observe A to B. The current direction is, when you're going from A to B, the current direction is also same. So give positive sign. So B to C, you're going from B to C, your path direction is B to C, so the current direction is also same, positive. Now when you're going from B to C, the first positive terminal have come across, so positive to negative is positive. Now from C to D, your path direction is C to D, the current direction is opposite, that is I3 is opposite to, okay, opposite to the path direction, right? So minus, right? So from D to A, the first terminal that you come across is negative, so minus to plus is minus E1. So and D to A, your path direction and the current direction both are same, so it is positive. So combining all these things, if you equate the sum to 0, then that equation is called as the KVL, Kirchhoff's voltage law equation. Using Kirchhoff's voltage law, the algebraic sum of the potential differences and EMFs in a closed path is equal to 0. Let me write that equation. Plus I1 R1 B to C, so I plus I2 R2, from positive to negative, so plus E2, from C to D the current is opposite, so minus I3 R3, from D to A the first terminal is minus to plus, so minus E1. When you go from D to A, the current direction is also same. So plus I4 R4 is equals to 0. So like this you can apply the Kirchhoff's voltage law in a given mesh, right? So applying these concepts and solving a mesh analysis problem. First, as identify the number of meshes, assume the current directions into the meshes. So the first mesh it is I1, the second mesh it is I2. The current in this particular branch is going from A to B. The current in this particular branch B to D, one side I1 is flowing from B to D, whereas I2 is going from D to B, right? So let us apply KVL in the first mesh ABDA. We get, when you go from A to B, 6I1 plus B to D, 3I1 minus I2. Why did I consider I1 plus and I2 minus is, you have to consider I1 as positive when you're writing the mesh equations for A, B, D, A, and any other current component should be given minus sign. If they are opposite, if they are in the same direction, consider plus. So as I2 is opposite to I1, so we have considered I2 as minus. So 6I1 plus 3I1 minus I2. So from negative to positive, minus 42 is equal to 0. Applying KVL in the second mesh, which is BCDB, we get 4I2 minus 2 plus is minus 10 volts plus 3 into I2 minus I1. Just now I told you, when you're writing the mesh equation for the second mesh, give importance to I2, give positive to I2, and the opposite current in the other mesh will be given negative sign. The same direction current should be given positive sign. Okay, so 3 into I2 minus I1 is equals to 0. Step number 4, which is the final step, solving both the equations. First one is the equation that we got by applying KVL in the first mesh. Second one is the equation that we got by applying KVL in the second mesh. Solving these two equations, you may use Cramer's rule or else any other method, elimination method, in solving both the equations. If you solve them, you will get the values of unknowns I1, I2 as I1 is equal to 6 amperes and I2 is equal to 4 amperes. So if you know the current in this particular branch, so the voltage drop across this is going to be 6 into I1. How much is that I1? 6 amperes. So the voltage drop across the 6 ohms resistor is going to be 6 into 6, 36 volts. 36 volts is going to be the voltage drop across that 6 ohms resistor. If you consider the voltage drop across 3 ohm resistor, I1 is I1 is 6 amperes, I2 is 4 amperes. So from B to D, I1 is 6 and I2 is 4. 6 minus 4 is 2. 2 into 3 is 6 volts. 6 volts is the voltage that we notice across BD resistor, 3 ohms resistor. Okay, like this you can apply mesh analysis technique in finding various currents in various branches and the voltage drops across various branches or components, uh, we apply mesh analysis technique in the next two more circuits with more number of branches and more varieties of combinations to understand this mesh analysis technique little more thoroughly. We will see those things in the next video, part 3. Thank you.